electrolytes, and nonelectrolytes. Nonelectrolytes are substances that do not conduct electricity when dissolved in water. Water, for that matter, is not an electrolyte. Here's a picture showing a light bulb that's hooked up by a wire to an electrode that's immersed in water. And then there's another electrode immersed in water, and this other electrode goes to a battery that then goes to the white wire. So, we know that pure water is not an electrolyte because we do not see the light bulb lighting up. In this second picture, again, the light bulb is not lighting up, although now we don't have pure water in the beaker, we have a sugar water solution. This means that sugar is also not an electrolyte. In the third picture, we can see the light bulb is lit up. The white wire goes to a battery, and then that battery is connected to the black wire, which is connected to an electrode immersed in a beaker of our electrolyte solution, and there's another electrode that goes to the light bulb. So the light bulb is lighting up, and the fact that the light bulb is lighting up means that electricity is being conducted between those two electrodes in the beaker. So this is what it means to be an electrolyte. Electrolytes are compounds that conduct electricity when they are dissolved in water. So, this begs the question, what is electricity? Normally we think of it as movement of electrons through a wire. So, coming out of the battery, we have electrons that are being pushed through the wire by the electrical potential. But it's not electrons that are jumping across the gap. In the beaker, once we get back to the wire, it's electrons again. And the electrons moving through the filament in the light bulb essentially make the filament very hot. When it gets hot, the electrons in the light bulb are excited, and when they fall back down, they emit light. But we know it's not electrons moving in the beaker. So what's going on in the beaker? Well, electricity doesn't have to be movement of electrons. Think about it. What is an electron? It's a particle that has a charge. So in fact, electricity can actually be movement of any charged particle. This means that a solution of electrolyte contains charged particles. And we've seen this. What kind of charged particles can be present in solution? The answer is cations and anions. For instance, this could be a sodium chloride solution. So there'd be Na plus ions and Cl minus ions present in solution. And as the electrons come through, the Na plus ions cluster around that negative electrode called the cathode, and the Cl minus ions cluster around the other electrode, which creates a charge difference, which causes electrons to flow. So going back to our definition, of an electrolyte being something that conducts electricity when dissolved in water, this means an electrolyte is any compound that produces ions in solution. There are three classes of electrolytes. I bet you all already know that ionic compounds are electrolytes. They will dissociate into ions in water. What are the two others? Well, acids for one. Acids ionize to make an H plus and an A minus ion, where A just stands for some generic anion. Another class of electrolyte is bases. Bases react with water to make a cation and a hydroxide ion. So, all three of these classes of compounds produce ions in solution. This table from your textbook shows some compounds that are electrolytes and some that are non-electrolytes. Let's put each of them into categories. For the electrolytes, we'll use our three categories: A for acid, B for base, and I for ionic compound. So going through these electrolytes, if it starts with H, it's an acid. So H2SO4, HCl, HNO3, HC2, H3O2, that's acetic acid. Those are our acids, okay? Now, as far as bases, sodium hydroxide is a base. It's also an ionic compound, right? You got a sodium ion and a hydroxide ion. NH3, ammonia, is a base. K2SO4, that's potassium sulfate. It's got potassium ions and sulfate ions, so it's an ionic compound. And NaNO3, sodium ions and nitrate ions, an ionic compound. Now, the non-electrolytes all tend to be molecular compounds. C12H22O11, sugar. C2H5OH, ethanol. C2H4OH2, ethylene glycol. C3H5OH3, glycerol. CH3OH, methanol. CO and H22, urea. O2 and H2O. Not all electrolytes are created equal. Some are strong, whereas others are weak. Let's define that. Strong electrolytes are present as 100% ions in solution. An example is sodium chloride. When you put sodium chloride in water, 100% of it separates into sodium ions, Na+, and chloride ions, Cl-. Another example is the strong acid, HCl. You bubble HCl gas through water, and all of it separates into H+ ions and Cl- ions. Right, so that's the picture on the left here. H+ ions and Cl- ions. There's not a single hydrogen chloride molecule left in solution. Weak electrolytes, on the other hand, are less than 100% ions in solution. So that means some unionized compound is present. An example of this is a weak acid. Like acetic acid, HC2H3O2, and we use a double-headed arrow to give us some H plus and some acetate ion, C2H3O2 minus, as you can see in this picture. Here is the unionized acid, as seen on the left. Here's the H plus ion, and here is the acetate ion. Now, looking in solution, what do we have? Well, we have some unionized acid. There's one, there's one, there's one, there's one. But we also have some acetate ions. There's an acetate ion, and there's an H plus ion. And for most weak acids, the percent ionization is much less than 100. So here we have many more unionized acid molecules than ions. That's what makes it a weak electrolyte. The concentration of ions in solution is too low to effectively conduct electricity. Here's a table summarizing strong and weak electrolytes. Strong electrolytes include most soluble ionic compounds: sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, perchloric acid, and then the strong bases: sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. We should also add to this HI, hydroiodic acid, is a very strong acid. That gives us 1, 2, 3, 4, 5, 6. There are actually 7 strong acids, and the 7th is HClO3. Right, so these are our strong acids. We use a capital A for strong acids. And then these soluble metal hydroxide salts are strong bases. We'll use a capital B. So, capital A, strong acid, capital B, strong base, and then let's go, little a is a weak acid, and little b is a weak base. So, acetic acid is a weak acid, carbonic acid, a weak acid, nitrous acid, weak acid, sulfurous acid, weak acid, hydrosulfuric acid, weak acid. Oxalic acid is a weak acid, boric acid. This guy kills ants. Also a weak acid. Hypochlorous acid, a weak acid. NH3, a weak base. Hydrogen fluoride or hydrofluoric acid, a weak acid. And the way you tell the difference in a chemical equation is the kind of arrow you use. For the ionization of a strong acid, you have your acid HA, AQ on one side, and a single-headed arrow to make H plus AQ and A minus AQ on the right-hand side. For a weak acid, the equation looks almost identical. Here's your acid formula, HA, and on the product side we get H plus ions and A- ions. So, what's the difference? The weak acid uses this double-headed arrow to show that the ionization is less than 100%. Therefore, the ion concentration in solution should be lower, and the conduction of electricity is not as good.